Swayam Prabha. Digital India. Educated India.
Hello friends, we are back with our MOOCs course on the topic of fundamentals of nuclear power generation. We have already gone through 5 different modules and I hope you are enjoying whatever lectures we had so far. In the previous lectures, we have covered the topics of neutron flux distribution inside the reactor and in the recently concluded module 5, which you have covered in the last week, there we discussed about the heat transfer aspects of a reactor. Now, today onwards we are going to start the 6th module, a topic I am personally very much excited about, that is on reactor control and associated kinetics. Now, if you remember carefully, in the 4th module you are introduced to the term a critical reactor, while in common English the term critical generally represents some kind of crisis or something, but here actually a critical reactor is the desired condition where for corresponding to each fission reaction only one of the product neutron can induce a subsequent fission. So, that the rate of fission or rate of neutron generation remains constant and accordingly we keep on getting a constant rate of power output from the reactor. Subsequently, in all those neutron flux profiles that you have derived in your module 5 and also the discussion related to heat transfer in module neutron flux distribution in module 4 and the heat transfer analysis that we have done in module 5, all them generally corresponds to the critical reactor only, because that is the desired condition. But there may be several situations, there may be several scenarios inside a reactor where we can't maintain the reactor either intentionally or unintentionally, we can't maintain it in the critical condition, rather we have to go for subcritical or supercritical situations. For example, you can think about, say, your reactor is operating at a critical condition giving constant rate of power, but now there is a sudden increase in the demand. So, you have to increase the power output from the reactor and that is possible only if somehow you can increase the rate of neutron generation, or I should say the rate of fission reaction. That means, at least for certain period of time you have to make the reactor supercritical, when the multiplication factor is greater than 1, reactivity is positive and the rate of reaction keeps on increasing with time. And once you reach the desired higher level, then you can get the reactor back to the critical condition and you can continue operate with that. Similarly, when we have to reduce the power output from a reactor, we must make it subcritical for a certain instant of time, so that the reaction rate comes to some lower level and then it can continue to be critical again. You can compare this with what we do while driving a car. Like in a long smooth highway, when you are driving at a constant speed, we can maintain a constant pressure on the accelerator, so that the fuel that is getting supplied to the engine, that remains constant, and so we get a constant speed of the vehicle, a constant power output, brake power output from the engine. But if we have to accelerate, then we must put some higher pressure on the accelerator, so that the fuel supply to the engine increases and engine keeps on producing larger amount of brake power. The opposite is true when we have to decrease the velocity or speed. So, there are certain situations, particularly for controlling the output from the engine, we have to make it subcritical or supercritical. There may be a further extension of that, like suddenly there is a situation where we have to stop the power out production from the reactor because of some emergency or maybe just a planned maintenance kind of situation. Then you have to make the reactor highly subcritical, so that the rate of reaction quickly decreases and finally it dies down to 0. So, these are generally the intentional situation, but there can be some long term scenarios as well. Like in a coal based thermal power station, we generally supply coal, that is the fuel, that continuously. There is some kind of coal handling unit which crushes the coal to some small elements, generally of the size of 75 to 100 microns, and those coal particles along with air is continuously fed to the boiler. But that we generally can't do in case of a nuclear reactor. Rather, we load the reactor with some desired quantity of fuel. You must remember the term critical mass. Critical mass refers to the mass of fuel required to make a reactor critical. So, we generally load the reactor with this desired quantity of mass and then keep it running for a long period of time. Long means really means long, which can be 6 to 12 months or even more than a year, and then only we again recharge the reactor with another set of fuel after that period is over. So, if you consider, say, at the beginning of this period, that is at the time of loading, we have supplied the critical mass to the reactor. That means, the reactor will operate as a critical one initially, but as we there will be not too much change in the quantity of fuel mass over a period of say 2 days or 5 days or maybe 2 weeks. But if you take a stock of the situation after 6 months, whenever there has to be some kind of reduction in the fuel quantity of fuel, because whenever a fission reaction happens, that corresponds to the destruction or depletion of one fuel nuclei or one fuel nucleus. So, the quantity of fuel continuously decreases as the reactor keeps on increasing power in producing power, and therefore, after a certain period of time there has to be a significant reduction in the quantity of fuel that is available to cause fission inside the reactor. Then the challenge is to still maintain the critical condition inside the reactor. If we initially fed the reactor with just critical mass, then after 3, 4, 5 months it must get reduced to the subcritical condition. So, we need some kind of controlling mechanism, so that we can maintain the reactor under critical condition both at the beginning of that loading period or when the reactor is freshly loaded, and also several months after that. There is another issue here. During the fission reaction, those parent nucleus gets broken into two daughter nucleus, and all those daughter nucleus, they are also, that is those fission fragments, they are also radioactive in nature. So, their subsequent degradation produces several kinds of isotopes, and initially the concentration of these isotopes are virtually negligible inside the reactor, but with time their concentration keeps on increasing, and certain of them are known as neutron poisons, like some of the isotopes of xenon, which has very high absorption cross section. So, once they start appearing inside the reactor, they can eat up a significant fraction of the neutron that are available inside the reactor, and once they absorb those neutrons, then the number of neutrons available to continue the chain reaction that keeps on decreasing. Now, you consider the scenario, one side we are having the fuel which is reducing, and on the other side such kind of neutron absorbing material, their concentration is increasing, and the net product of these two has to be a reduction in the reactivity, a reduction in the effective multiplication factor. So, we need a proper controlling mechanism by virtue of which despite all these scenarios, that is decrease in fuel, increase in neutron poison, we can still get a significant amount of power production from the reactor, or preferably we can maintain a critical condition inside the reactor. That is what we are going to discuss in this particular chapter. That is firstly from a mathematical point of view, we shall be setting a background, seeing mostly the role of prompt and delayed neutrons on the reactor control, and then we shall be seeing different ways how we can control the reactivity inside the reactor. Next is the time dependent reactor. Virtually whenever we are dealing with a critical reactor, we can deal that as a steady state situation, because the neutron flux and hence the power output that remains constant with time, and so we can neglect the time derivative of any component. But whenever you are dealing with a subcritical or supercritical reactor, definitely the neutron flux and the rate of fission reaction and also the rate of power generation, that keeps on changing with time, and so we have to consider this as a time dependent problem. But from nuclear kinetics point of view, time dependent problems can be divided into 3 categories. The first one is the short time problem, where the time interval under consideration generally ranges from seconds to tens of minutes, and these are the kinds of problems where we completely neglect the depletion of fuel, that is the mass of fuel is considered to be constant, and these are the problems that we generally use while solving reactor transients and also the safety analysis. There can be next the intermediate time problem, where the time span can be a few hours to even 1 or 2 days, typically up to 2 days. Here also quite interestingly we neglect any depletion of fuel. However, the production of the fission products that needs to be considered, because over a period of 2 days the concentration of certain fission products can have significant amount of increase. So, that changing characteristics of the fission products needs to be considered, but again here also similar to the short time problem, we can consider the fuel mass to be constant. And third is the long time problem, where we are going for a very long period, certain weeks to several months. Here we have to consider the changing characteristics of fuel, changing stock of fuel, and also the change in the flux and fuel distribution inside the reactor. Because as we have seen in the neutron flux distribution in module 4, the neutron flux, while we would like to have that uniform, that generally is not uniform inside the reactor. Particularly if the reactor is not a reflected one, then the neutron flux will be extremely low at the edges and very high at the center line. Therefore, the fuel which is present close to the center line or the zone where the neutron flux is high, that will experience larger amount of fission, and so the depletion in fuel there will be much more compared to the depletion in fuel in certain other areas of the reactor. That also needs to be considered in these long time problems. But here our objective will mostly be surrounding to this short time and intermediate time problems, at least in this chapter. Now, the interesting part of that short and intermediate time problems is that depletion of fuel is neglected. But the question is, how can we neglect the depletion of fuel over a period of 2 days? Virtually we are considering the mass of fuel to remain constant, but still we are getting power output. And to justify that, we need the concept of fuel burn up. Fuel burn up refers to the rate of consumption of fuel typically over a single day in a given reactor. That is the amount of fuel a reactor consumes in one single day, that is called fuel burn up, and this is a term not exclusively used for nuclear reactors, but can be used for any kind of power generating entities. So, let us take one example. We are considering a reactor which is giving 500 megawatt of output, and it has initially been loaded with 250 tons of natural uranium. Now, if you remember, natural uranium basically comprises of 3 different isotopes, primarily uranium 238, which is which comprises more than 99% of this. But uranium 238 is a fertile isotope, so it does not undergo fission, at least when it is subjected to thermal neutrons. It has a very small fast fission cross section, but can be neglected generally in thermal reactors. Here our point of interest is uranium 235, but its fraction is only about 0.7%, because this is a fissile one, and therefore, it is only this uranium 235 which can produce power by virtue of this fission reaction, and small amount traces of uranium 234 can also be present. So, first we need to identify the mass of uranium 235 that is present in the core. Total mass is 250 tons, but that corresponds to the natural uranium. And then we need to know first the mass fraction of uranium 235 in this reactor, and that mass fraction can easily be calculated, as we know the molecular weight or atomic weight rather of all these 3 isotopes and also their percentage. So, the fraction of uranium 235 can be calculated as 0.72 into its atomic weight 235.04. I am not writing the further digits, divided by the same for all the components, that is for U 234 is 0.0055 into 234.04 plus 0.72 into 235.04 corresponding to uranium 235 plus the last fraction for uranium 238, which is 99.27 into 238.05. So, do the calculation, it will come to be at 0.00711, and once we multiply this mass fraction with the total mass of the fuel, that is 250 tons, then we get the amount of uranium 235 available inside the reactor to be only 1.7774. So, this is the mass of actual fuel that is available inside the reactor, but actually the total mass of substance that we have supplied is 250 tons, but our calculation we shall be doing with respect to the mass of uranium 235 only. Now, we know that the total amount of energy released during the fission reaction of uranium 235 can have several components. This is a chart that was shown in the earlier modules, and it is roughly can be said that we get 207 MeV of energy because of the fission of a single uranium 235 isotope. So, the total amount of energy that we are getting because of the fission reaction can be this 207 MeV for a single nucleus, this multiplied by 1.602 into the minus 19, where we are considering this energy to converting this energy to megajoule, and then it is 6.0221 into 10 to the 26, that is the Avogadro number, which converts this from single nucleus to 1 kilomole. And so, these three quantities is a product of these three numbers gives you the amount of energy that is being released by 1 kilomole of U235, and the unit of that is this megajoule. And next, if we divide it by the molecular mass of uranium 235, then we get the total output as from per kg of fuel. So, we are getting 84.9 into 10 to the 6 megajoule of energy from a single kg of uranium 235 alone, and total quantity that we have supplied is 1.7774 tons. So, the burn up then can be calculated as 500 megawatt is the thermal output that we are getting, divided by the amount we are getting from a single kg of this, which comes to be something like 5.88 into 10 to the minus 6 kg per second, or just half of a kg in a single day, which is a staggering number really. That is 500 megawatt of energy we are getting, and to get that amount of energy we have to spend only half kg of uranium 235 in a single day. So, if we want to calculate the change in the percentage change in the amount of uranium 235 inside the reactor over a period of 2 days, then we can calculate this the amount of fuel consumed in single day multiplied by 2 divided by the total mass available, and just 0.57% or 0.057%, that is less than 0.06% change in fuel mass will happen over a period of 2 days, and that is why we can neglect this depletion of fuel mass in short time or intermediate time problems. Just to consume 1% of this total mass of fuel, that is this one, just to consume 1% of this one we need something like 34 to 35 days. That is why once we have loaded our reactor with this 250 tons of natural uranium or 1.7774 tons of uranium 235, we can keep on running it for a long period of time. Theoretically, as 1% is consumed in about 35 days, so it can go up to 3500s. It can go up to 3500s, that is more than 9 years without any further fuel loading. Practically, that is of course not done because of several other reasons, but still once we have loaded the reactor with a certain quantity of fuel, we can keep on using that for a long period of time. Just if we would like to take this one or compare this one with a conventional coal based power station. In a very good quality bituminous coal that we use nowadays, the typical calorific value is generally of the order of 30 megajoule per kg. So, this is the typical calorific value of common bituminous coal, it is a high grade coal, and if we use this particular coal to get the similar thermal power output, then how much energy you have to how much amount of fuel you have to produce or we have to supply. You can do the calculation, you know that the total output is 500 megawatt and 1 kg of coal is giving you about 30 megajoule. So, if you compare this, you will find that corresponding this number corresponds to this is will be coming something like 1400 tons per day. Actually, it will be greater than 1400 tons per day. That means, while in to get the same amount of power, while we are spending just 0.5 kg of uranium 235, we are spending more than 1400 tons of coal, and that is also a good grade coal. If we compare this with say natural gases, gases may have a higher calorific value, something in the range of 50 megajoule, still the total amount consumed will be 1000 tons for a single day. And that is the reason the amount of fuel requirement in a nuclear power station is much lesser compared to a conventional coal based power stations, and hence the total volume of the reactor can be much lesser compared to a coal based one. Next we move to the prompt and delayed neutrons. These two terms were introduced earlier itself in one of the earlier modules, and we clearly know that prompt neutron refers to the neutrons which are produced directly from the fission, and therefore, they appear within 10 to the minus 14 seconds of fission occurrence. Whereas, delayed neutrons actually are the result of the radioactive decay of certain neutron rich fission fragments. Generally, fission fragments undergo beta decay, because of which electron comes out of the fission fragments and they get converted to a different isotope. But in certain fission fragments or during those decay chain of those fission fragments, we may sometimes encounter certain neutron rich elements, and those neutron rich elements can undergo neutron decay, and those neutrons are called delayed neutrons, and the isotopes which leads to the formation of these delayed neutrons are known as delayed neutron precursors. Appearance time for this delayed neutron depends upon the decay rate of these delayed neutron precursors, and it can range from a few milliseconds to something of the order of 50 seconds as well. Presently, the longest living delayed neutron precursor is bromine 87, which has a half life of about 55 seconds, or the mean life of about 55 seconds. And presently, both from nature and also through laboratory controlled experiments, we have identified about 240 numbers of such precursors. It has a very wide range. It can have very low mass numbers such as helium 8 to a high mass number like thallium 210, and several of them are actually outside the fission range, that is their atomic number is quite small to cause any kind of fission, but still like this helium 8, this kind of very light isotopes can also act as delayed neutron precursors. Now, total amount of neutrons that are available from fission, more than 99.9% are prompt in nature. So, the total number of delayed neutrons or total fraction of delayed neutrons that is available is extremely small, and also that keeps on depending on the nucleus itself and also the energy of the neutrons. Like this is a chart that I am showing. If you compare the values for uranium 235, then for thermal fission, whereas the number of prompt neutrons, average number of prompt neutrons is 2.42, corresponding number for delayed neutron is just 0.016. It is an extremely small percentage, and the same is true for others as well. Like you can think about plutonium 239. Plutonium 239 has a very high fission cross section, and it can produce on an average 2.87 number of prompt neutrons for every thermal fission, but corresponding number of delayed neutrons is extremely small, 0.0065. So, the total fraction of delayed neutron that may appear during a fission reaction is extremely small compared to the prompt neutrons, and also as they appear way after the actual fission occurrence. So, their energy level is also much lesser. Like the fission reaction, the concerned fraction that of delayed neutron that may appear, that can decrease a bit with the fuel burn-up because of the change in the isotopic change in the fuel concentration. But from energy point of view, prompt neutron can have very high kinetic energies, can range from 0.1 to 10 mega electron volt, because they are directly getting a share of the energy released during fission. On an average, prompt neutrons come with an energy of 2 MeV, or at least for a calculation purpose, generally we consider a prompt neutron to have on an average 2 MeV of energy. And if we compare that figure with the delayed neutrons, it is just 0.3 to 0.9 MeV. So, much lower compared to the prompt neutrons. For delayed neutrons, the average is something like 0.4 MeV. So, 2 MeV for prompt neutrons, whereas only about 0.4 MeV for delayed neutrons. Prompt neutrons have very important role in the physical characterization of the core, but delayed neutrons, the question definitely is coming to your mind that while it is such a small fraction, less than 0.1%, sometimes even lesser like we can always compare these numbers like 2.87 and 0.0065. So, it is such a small fraction, why we at all need to bother about the delayed neutrons. But as we shall be seeing shortly in this lecture and also in the next lecture, the delayed neutron play a very important role in controlling the reactor. In fact, it is only because of the delayed neutrons we can successfully control a nuclear reactor. Otherwise, if we are depending only on the prompt neutrons, it would have been a hell, it's an extremely difficult job to control a nuclear reactor. Yes. Thanks to the delayed neutrons, we can do that quite successfully. Now, come define the prompt neutron lifetime. Prompt neutron lifetime is defined as the average time elapsed between the generation of a prompt neutron through fission to its absorption by the fissile material for the next fission. That is, a prompt neutron, the moment it appears from a fission reaction, we start calculating this lifetime. It goes through several levels of phenomena, like it can in very rare cases it can induce a first fission, it can go through all those scattering and attenuation through the intermediate energy range, and finally, once it comes to the thermal neutron level, it can get absorbed, it can get diffused through the thermal neutron as well, and it can get absorbed in the moderator or in the fuel, and this entire period is the one that we call as the prompt neutron lifetime. And mathematically we use this symbol LP to call the prompt neutron lifetime. Of course, generally time is denoted by symbol T, but this is a convention that we generally follow. So, the two typical phenomena a prompt neutron undergoes is the scattering and also the diffusion. Scattering through the moderator and also the diffusion process that after getting thermalized. Here Ts refers to the scattering time, which is the average time required for the neutron to slow down in the moderator. Td is the diffusion time, that is after becoming thermalized is the time it spends inside the reactor. Typically the scattering time is of the order of 10⁻⁻7 seconds and diffusion time is of the order of 10⁻³ seconds. We shall be calculating them shortly. Let us try one case, that is the typical diffusion time can be defined as lambda A by V average, where lambda is the absorption mean free path of the thermal neutron inside the reactor and V average is the average speed for the thermal neutron. And as lambda A is inversely proportional to the absorption cross section of thermal neutron in the core. So, we can always write this. Here again I would like to mention lambda refers to the absorption mean free path, and so sigma SC corresponds only to the absorption macroscopic absorption cross section, and V average is the average speed of the thermal neutron. Next, this small f we have defined earlier, this is the thermal utilization factor. So, thermal utilization factor is a macroscopic cross section of the fuel divided by macroscopic cross section of all other elements that is present there. Macroscopic absorption cross section of fuel divided by macroscopic absorption cross section of all other elements. This is after becoming thermalized. Here we are considering only fuel and moderator. So, F is equal to sigma for absorption for fuel divided by sigma absorption for fuel plus moderator, and hence 1 minus F is equal to sigma of A for moderator divided by sigma A for the core, that is the total macroscopic absorption cross section, and hence Td can be written as 1 minus F by V average into sigma absorption for the moderator. And the same way we can calculate for Ts as well. It is equal to lambda S by V average S. Lambda S is the scattering mean free path and V average S is the average velocity of the neutron during the scattering process. One thing, this velocity during the scattering process definitely keeps on changing, because the only energy that neutron can have is the kinetic energy, and during the scattering process its kinetic energy reduces from something like 2 MeV to 0.025 electron volt, and therefore, accordingly this V average can also have a very large range. So, lambda S can be related to the macroscopic scattering cross section for the moderator. It is a moderator where the scattering process is going on. Fuel does not have any role in the scattering, and that is why we are having only the moderator here. And now, we use these energy ratios. Here En thermal, the denominator refers to the energy of a thermal neutron, and hence it has to be half into mass of a neutron into the average velocity of the neutron during the diffusion process, and the numerator ENS bar, that refers to the average energy during the scattering process. So, it has to be equal to half V average square, and from there we can get an expression of V average scattering and relate that to V average diffusion. So, once we put this final expression, we get this as the final expression for the scattering time. So, now we have derived both the expressions for the diffusion time and scattering time, and let us put them together or add them together to get the prompt neutron lifetime. Let us take the example of a graphite moderated reactor where the utilization factor is 0.9. For graphite, we know the microscopic absorption and scattering cross sections and also the density. Once we know the density, we can use that to calculate the number of such nucleus present inside the moderator per unit, or number of moderator nucleus present per unit volume, which can be the density into the Avogadro number divided by the molecular weight of graphite, and accordingly it comes to be 8.1298 into 10 to the power 28 number of nuclei per unit volume. Now, macroscopic cross section is this number of nuclei per unit volume or nucleus density multiplied by the microscopic cross section. So, accordingly this one is the macroscopic absorption cross section for the moderator. And for a typical thermal neutron, the velocity is generally around 2200 meter per second, because its energy is something like 0.025 electron volt. So, the expression for TD is already known to you. We are putting these numbers that we have calculated and putting them, we are getting it to be 1.2 into 10 to the minus 3 seconds or something like 1 millisecond. That is the diffusion time. Now, let us calculate, okay, these are the typical diffusion times for some common moderator, whereas it is just of the order of 10 to the minus 2 for D2O with 0.25% of impurity. It is only 10 to the minus 4 compared to water. So, the diffusion process in moderate depends the rate of diffusion process depends on the nature of the moderator itself. Now, you go to the scattering plot. Similar to the absorption, you can also calculate the macroscopic scattering cross section, which is something like 32.21 per meter, definitely much larger compared to the absorption process. And the energy for a thermal neutron is 0.025 electron volt. Then energy for average energy during the scattering process, it should be average energy bar should be there are several ways we can calculate this, but here going for a simple approach. Initial energy at the starting of scattering can be taken to be 2 mega electron volt, and at the end of the scattering process, when it has become thermal, its energy is 0.025 electron volt. So, the average of that is 1 mega electron volt. So, we put that into the mathematical expression for scattering period, scattering time, and is coming of the order of 10 to the minus 9 seconds only. So, this diffusion time and scattering time, there is a very large difference between them. While diffusion time is of the order of only 10 to the minus 3 second, scattering time is of the order of 10 to the minus 9 second. And therefore, for thermal reactor at least, the prompt neutron lifetime is considered to be equal to the diffusion time only. The scattering time can safely be neglected. Now, we have to apply the one group diffusion equation on an infinite thermal reactor. Here the reactor is infinite, and we are considering from the previous slide whatever we have done, we are taking this prompt neutron lifetime to be equal to the diffusion time, and also we are neglecting the presence of any delayed neutron from any source. So, this is the equation that we have dealt with earlier also. The rate of change of neutron density should be equal to the production rate minus absorption rate minus leakage rate. As we are considering an infinite reactor, so there is no leakage, then we are having only production and absorption. Accordingly, this is the equation where S is the production rate and this is the absorption rate, and finally this is the leakage rate, but this leakage rate of course will be equal to 0. So, the equation reduces to this particular form. Here the neutron density n, as we are considering an infinite reactor, infinite thermal reactor, so we can neglect the variation in neutron density in different parts of the reactor, and so n becomes a sole function of time only. The absorption and the production rate can be related like this, and phi is known as n into the average velocity, that is the neutron density into the average velocity of the neutron. So, we again know that just from the previous slide we have seen that LP is equal to 1 by the absorption cross section into the average diffusion velocity. Accordingly, this equation, this LP terms comes into play. That is, our equation reduces to dn dt is equal to k infinity minus 1 by LP into n. Putting this into perspective now, we can rearrange the terms and we can perform this integration to get expression of n t equal to n naught in the exponential k infinity minus 1 into t by LP, where n naught refers to the neutron density at time t equal to 0, or n t equal to n naught into minus t by capital T, where capital T is LP upon k infinity minus 1, that is, which is called the reactor period. It is called the reactor period. If we now assume a situation, another test case that we are considering a reactor which is initially operating as a critical one, that is, the effective multiplication factor is 1, but because of certain disturbances it has increased by a very small fraction of 0.1% and it has become 1.001. If we put this number into this expression, firstly we have to calculate capital T. We know that this from our previous analysis, this LP is of the order of 10 to the minus 3 and k infinity after modification is 1.001. So, capital T is of the order of 1 seconds only. And now, if we put it in perspective, taking small t equal to 10 second, then NT becomes, after 10 second, becomes 22,000 approximately of the initial neutron density. That is, just over a period of 10 seconds, the number of neutrons present inside the reactor will increase by 22,000. That is an extremely large number. As the number of neutron keeps on increasing, corresponding reaction rate keeps on increasing, and just in 10 seconds the reactor will produce, if it at all can survive such rate of such high rate of increase, then it will produce 22,000 larger amount of power compared to the original reactor. So, that is a situation which is extremely difficult to control and we have to find some other mechanism, and that is where the role of the delayed neutrons comes into play. Delayed neutron, as I have mentioned, are the outcome of the radioactive decay of these fission fragments. During some of the fission fragments during their decay can appear to be neutron rich in nature, and therefore, they may lead to the emission of neutrons. Like one chain is shown here for bromine 87, it has a half life of about 55 seconds. Now, during its decay commonly it produces krypton. Now, krypton again there can be several kinds of isotopes, like if we consider this one where krypton is 87 star, means it is an excited krypton 87, then it can undergo a gamma decay to come back to just normal krypton 87, and then it can go through 2 levels of beta decay to finally reach HR 87. But there can be other routes also. By undergoing beta decay, it can also produce krypton 87 which are normal isotopes, not any excited stage like this. Now, krypton 87 is something that is neutron rich, and therefore, it is very likely to emit a delayed neutron and become a stable krypton 86 isotope. So, while most part of this chain corresponds to either beta decay or gamma emission, only one chain originating from bromine 87 can lead to the formation of delayed neutrons and krypton 86, the stable isotope. Here is another example with iodine 137. It has a half life of 24 seconds, and again it can go to beta decay to produce either xenon 137 or xenon 137 star, that is excited. Xenon 137 goes through 2 levels of beta decay to reduces to Ba 137, barium 137, but it is also possible, like here this excited stage, its energy content is so high that it can dislodge one neutron from its nucleus, thereby giving this particular delayed neutron. And final product is xenon 136. There are two terms which are commonly used while dealing with delayed neutrons. One is the delayed neutron fraction, which is defined very straightforward definition, delayed neutrons delayed neutron fraction is equal to delayed neutrons divided by total number of neutrons, that is prompt plus delayed. But there is another definition which is used, that is beta. This is this is slightly different, where in the numerator we have the precursor nuclei, or delayed neutrons basically has been replaced by precursor nuclei. Beta is equal to precursor nuclei divided by precursor nuclei plus the prompt neutrons. Generally both of them are same, but when the situation where there is a rapid change in the neutron flux distribution, then both may become identical. Here also we shall mostly be dealing with delayed neutron, but here also we shall mostly be dealing with the situation where the neutron flux change is not that rapid, and so we shall be considering these two factors to be equal, that is beta and the delayed neutron fraction will be considered to be identical. Now, there can be several kinds of delayed neutron precursors which are produced during this nuclear fission and also subsequent radioactive decays. Like I have shown a number earlier, it can be as large as 240 and still increasing because of the newer elements found in the laboratory or newer compounds found in the laboratory. But it is not possible to consider all those isotopes separately. Like if I go back to the previous slide one, just take a look at this chain for bromine 87. There are how many isotopes involved? We have one bromine 87, this Kr 87, then number 3 Rb 87, then Sr 87 and also Kr 86. There are 5 isotopes which are involved into this. Similarly, in the other chain I 137, Xc 137, Cs 137, Ba 137 and Xc 136. So, again 5 here. That means, for successful modeling of that particular kind of chain, we need to consider at least 5 isotopes only for this kind of chain, and there can be much longer chains which involve several kinds of isotopes, and therefore, it is not possible to treat each of such isotopes separately. Rather, G.R. Kipin and his co-workers has proposed to combine these isotopes into 6 groups. These groups are formed based upon their decay rates and half-life, that is similar kind of properties. That is, Fu precursors which are having similar kind of properties are clubbed together into a single group, and then the property for that group is estimated by nonlinear least square fitting of the concerned experimental data. So, the property values for a single group may not match with any of its constituents, but it will give an overall behavior of that particular constituents. This is the groups that we can get for uranium 233. You can clearly see there are 6 groups and corresponding average decay constant and the fraction of that group, that is beta, that they are clearly given. Similarly, these are the groups for uranium 238. So, in case of uranium 233, you can see that only 0.0026 is beta fraction. So, that is 0.26% of total neutron is this delayed neutron. Similarly, it is 0.0065 for uranium 235, and this is the chart for plutonium 239. Here the delayed neutron fraction is only 0.0021. These are some examples of the isotopes which can appear in different groups, like the first group which corresponds to the lowest decay constant and hence the largest half life belongs to cesium 142, bromine 87, etc. The second one also deals with iodine 137 and bromine 88, and in the third case there can be several kinds of isotopes like iodine 138, rubidium 93, rubidium 93, rubidium 94 rather, and bromine 89. You can clearly see there are on all these 3 examples we have bromine isotopes involved, bromine 87, 88 and 89. We can also have bromine 90 and 92 in the 4th group, along with xenon 143, iodine 139 and a few others. And in the 5th group we have cesium and iodines, etc. There can also be an 8 group version of this, because the adoption of the 6 group model, the calculation that we get by adopting a 6 group model can differ quite a bit compared to the experimental measurements. So, to make this distribution more uniform, certain cases 8 group versions are also used. This is the 8 group version for uranium 235 and this is the corresponding version for uranium 238. You can clearly see the difference between them. In case of uranium 235 with 6 groups. The largest half life that you are encountering is 55.9, it is 55.6 only in this particular case. So, they are quite similar, but as we move down this table there is difference. Like for 6 group case, second group has an average half life of 22.72, but that has been broken into 2 parts into the second and third group for 8 group model. There are 3 isotopes which are having the longest half life, like bromine 87, iodine 137 and bromine 88, and they are the first 3. Those will be considered into separate groups. Like the first group for 8 parameter model is just uses bromine 87, or it has bromine 87 as the single component. So, all the half life and other values that are given corresponds to bromine 87 and not averaged with some other element. Similarly, second one uses the data for iodine 137 and third one uses for bromine 88. Just for your information, in certain situations we may have one delayed neutron precursor which is emitting not 1 but 2 neutrons, and even there can be situation when it can emit 3 neutrons also. There are at least 4 elements, 4 isotopes which can emit 3 neutrons. Like check lithium 11. Now, normal isotope for lithium is 3 Li6 or 7, and here then its mass number is 11, out of which 3 is proton, then there are 8 neutrons. So, we can clearly see for the others also. Accordingly, they need to emit very large number of neutrons to come back to some kind of ground states, and hence we get this 2n and 3n emitters. And before we close in on delayed neutrons, I would like to introduce another term called photoneutrons. Here these neutrons are not the resultant of direct radioactive decay of the fission fragments, rather they are produced by gamma n kind of reaction. I hope you remember this convention. It refers that the parent nucleus has absorbed one gamma photon and it has gone through a neutron decay process. That is, the daughter is actually another isotope of the same element, but its atomic number, while it remains the same, its mass number will be 1 less, because there will be 1 less neutron. This happens particularly when deuterium is the moderator. Here actually the gamma photon means whenever a gamma photon strikes a nucleus, these photoneutrons will not be emitted, rather the gamma photon should have sufficient energy so that it can dislodge 1 neutron. That is, the energy of the gamma photon should be larger than the binding energy of a single neutron. There are certain elements or certain nucleus whose binding energy per nucleon is quite low, and when that is hit by a photon of sufficient energy, it can lead to the emission of photoneutrons. But these are quite a few examples. Like you can see for deuterium, we have calculated this one earlier into our first module. The deuterium, the binding energy per nucleon is a very small number, just 2.225 MeV, and whenever it is being hit by a gamma photon of energy something like say 2.23 MeV or 2.3 MeV, then it will lead to the ejection of 1 nitrogen and the deuterium gets converted to normal hydrogen. And look at this example of beryllium 9. It is having an extremely low binding energy, probably one of the lowest among all known isotopes. It is just 1.667, and therefore, it is very easy to extract 1 photoneutron from this beryllium, and that leads to the formation of beryllium 8. But from characteristics point of view, these photoneutrons are found to be quite similar to the thermal neutrons and or normal delayed neutrons, I should say, and therefore, they are not distinguished from the delayed neutrons, rather during calculations or during analysis, photoneutrons are considered as a part of the delayed neutrons themselves. Finally, we shall be starting briefly the delayed neutron kinetics today, which a mathematical base we shall be setting up today, and we shall be finishing up in the next class. Let us again consider an infinite thermal reactor such that LP is nearly equal to TD. Here, Like earlier case, we consider all neutrons to be of prompt in nature, but here beta fraction of the total number of neutrons are coming in the form of coming from the delayed neutron precursors. There can be 6 different groups of precursors, we can consider 8 also, that will the analysis will remain the same. Now, the rate of change of neutron density, the same equation, it is equal to production and minus absorption minus leakage. There is no leakage for an infinite thermal reactor. But now production, while earlier we were considering production only because of the fission caused by from neutrons, here we can also have production because of the decay of the delayed neutron precursors. So, that need to be taken into consideration. So, this is the equation that we are having here. Here actually in this equation there are two parts. One part K infinity into sigma into phi thermal is the one that is coming because of the prom neutrons, fission caused by prom neutrons, and K infinity into beta into sigma AC into phi thermal is coming from the delayed neutrons. Actually, I should not have written this way. This is not the proper way of writing this. Sorry for that, just strike out what I have told earlier. This total number of neutrons, if we consider total number of neutron is 1, then out of that 1 minus beta comes from prom neutron and beta comes from delayed neutron. So, therefore, total rate of fission caused by prom neutron should be the number of fission reaction that is happening because of the prom neutron is 1 by beta into sigma AC into phi thermal. This is the number of prom neutrons that get absorbed and is about to cause a fission reaction, and once we multiply this with the multiplication factor, then that gives you the number of prom neutrons produced because of fission. And the second production part, that is the decay of delayed neutron precursor, is this. Here lambda is the decay constant for the ith group of precursor, the average decay constant, and C is the concentration of that ith group. And finally, we have the absorption rate here. Now, phi we know can be written as the neutron density into the average velocity of neutrons. So, this change has been done here. Phi has been replaced by n into V absorption for V average for this diffuse neutron. And now, we know that LP is equal to 1 upon sigma AC into V average D. So, that has been introduced here to write or replace the product of sigma AC into V average with 1 upon LP. Now, a little bit of mathematics. We are taking this numerator here and also combining that with this. So, K infinity 1 minus beta minus 1 can be written like this. And what is the definition of rho, reactivity? Rho we know is defined as K infinity minus 1 by K infinity. So, that substitution has been done, and accordingly we get this to be rho minus beta into K infinity. So, if we substitute that into our equation, then this is the final equation for the neutron density that we are getting. Here on the left hand side, d and dt represents the rate of change of neutron. In the right hand side, first one combines the production from the fission from neutrons and also the absorption, and the second term corresponds to the decay of the delayed neutron precursors. Now, delayed neutron conservation of the delayed neutron precursor must also be considered, because here this C term is unknown. While others are generally properties, we also need to know this C, and that is possible only if we consider conservation of these delayed neutron precursors. So, for the ith group of precursors, we can write this conservation equation where the left hand side represents the rate of change in the concentration of the ith group, and on the right hand side the first term represents the rate of production of delayed neutron precursors, that ith group, because beta is the delayed neutron fraction for that ith group, and lambda ICI represents the decay rate, which we have used in the previous slide also. And so, we can rewrite this thing into this form where I can vary from 1 to 6. Actually, if we consider 8 group model, then I will vary from 1 to 8, but generally 8 group model is quite complicated. In 6 group itself we have to deal with 6 different precursor groups and their properties. In 8 group the complexity is even more. So, we generally are sticking to the 6 group model. But here we are going to do a very simple analysis. If we are dealing with 6 group models, then you have to consider there was one equation for neutron density, and now there are 6 equations for the concentration of delayed neutron precursors. So, there are total of 7 equations in the framework, which is not possible to solve in simple analytical framework of a class. So, we are combining all these 6 groups together into a single group where the total delayed neutron fraction is beta, decay constant is lambda, and total concentration is C. Remember, C refers to the summation of Ci, where I is varies from 1 to 6, and similarly the lambda and beta can be calculated as the average quantities for all the 6 groups together. So, these are the 2 equations. Note out the change here. This is the change where instead of the summation we are writing as lambda into C, where lambda is the average decay ratio for all the delayed neutron groups together, and C is their concentration, and the second equation is the counterpart of this one. Now, we assume a solution of this particular form, n equal to a into t to the power omega t and C is equal to b into t to the power omega t. Here a and b are 2 coefficients and omega is the parameter which we are looking to identify. So, once we put it into the first equation, then it reduces to form like this. You please try to do it on your own, and similarly for the second equation. Now, e to the power omega t can be striked out from both sides of both the equations, and now we take everything on one side and we combine it into a form like this into a plus this into b is equal to 0. Similarly, for the other equation also, and we arrive at this particular matrix form, yes, where we have omega, lambda, rho and beta, and also k infinity involved, and definitely you have the prom neutron lifetime LP. So, this one will help us to identify the expressions for a, b and also omega. The solution of this one is the thing with which we shall be starting our next lecture. So, hopefully you have understood the discussion here. Today we have discussed about the concept of prom neutron lifetime, and we have also discussed about the role of delayed neutron. We have seen that if the neutron kinetics is solely governed by prom neutrons, then we have extremely small time to operate any kind of control devices. But as we shall be seeing in the next lecture, it is only because of the delayed neutron we are allowed to have larger amount of time, and hence we can control a nuclear reactor quite easily. So, that is it for the day. Thanks for your attention.